Okay, great. Welcome, everybody. I'm, as always, Sam Burden, Assistant Professor here in Electrical and Computer Engineering. And it's my pleasure today to be hosting our colloquium speaker, Professor Marcia O'Malley. So Marcia is an endowed professor in mechanical engineering, computer science, and electrical and computer engineering at Rice. And she directs a lab on mechatronics and haptic interfaces, the MAHI lab, like the fish. She's also the Director of Rehab Engineering at a big hospital in the Houston area. Her research focuses kind of broadly on the interaction between humans and robots. So aspects of that are what's called in the field human-robot interaction, but also robot-assisted rehabilitation. And then, which we'll talk about today, is really the direct physical mechanical interface, the haptic interface between people and machines. She's a fellow of the ASME and of the IEEE, and she serves as the associate editor in chief of IEEE Transactions on Haptics and senior editor for the transactions on Mechatronics and the ACM Transactions on human-robot interaction. So she is in charge of a lot of, of the field, and is just a fantastic leader and a wonderful speaker. So with that, I'd like to give the table over to Marcia.
Thanks, Sam. I really appreciate the opportunity to speak, to teleport over to Seattle for the day, and get to talk with some of your faculty, and nice to see your faces. I'm going to share today, like you said, some recent work in multi-sensory haptics. But first I have to, you did a nice overview. I'm going to do a little bit more overview of some of the broader things that we do in my group. So the MAHI lab named, so my husband grew up on the Gulf Coast and he likes to fish. So when we moved to Houston and I had to come up with a lab name, which is like Topo, it's one of the most stressful things ever, is to come up with a good acronym. I'm not sure if mine is a good one, but it is what it is. So Mechatronics and Haptic Interfaces. So all my training is in mechanical engineering, but the application areas that I'm interested in is how we can use the haptics and the physical interaction between humans and robots for basically enhancing and augmenting human performance. So the three areas that are kind of dominant in my group are haptic feedback for performance enhancement and training, and that'll be sort of the theme of today's colloquia. Exoskeleton robotics for upper limb rehabilitation, and then the more general physical human-robot interaction. So all my teaching is in dynamic systems and controls, robotics and mechatronics, and that really comes through with sort of the approach that we take to the problems that we like to solve. Yeah, I'll just skip that. And I'd like to highlight, so what do I think makes my lab unique, or my approach unique, is that I really love collaborating, and the more diverse the fields of collaborations, the better. So time permitting, you should ask me about my collaboration with an anthropologist and a religious studies poet, because that's a really fun story, but not relevant to today. But I really like bringing in the different perspectives and ways of sort of seeing the problems that need to be solved. Kind of complementary to that, we do a lot of work in healthcare and medicine. And so I want to be solving problems brought to me, as opposed to coming up with solutions that are looking for problems. And we do a lot of human subjects research in my group. With the current situation, it's been a little challenging, but we're actually back up and running with human subject studies. As long as our participants are in the Rice community, we're allowed to do that now. And so not only are we sort of evaluating our haptic devices and our haptic feedback at the end of how it affects human performance, we also like to bring our end users in during the design process. So I'll do just a little bit of self-promotion slides with pictures. So on the exoskeleton robotics side, as a mechanical engineer, I have to design hardware, right? So we design a lot of different devices for the upper limb. The ones that are shown kind of in the right side are all devices we designed and built in my lab. So exoskeleton devices for upper limb rehabilitation. And then these two, the glove and the suit here, were collaborations with Johnson Space Center, which is just down the road from me here at Rice. And these are sort of like hybrid, partially soft, partially rigid devices, also for supporting upper limb movement. So we design the hardware, we fabricate, and we implement control algorithms, and then we do the end testing to determine how those control algorithms affect people's ability to improve their motor coordination following neurological injury like stroke or spinal cord injury, or also just to support movements or train new skills as well. On the haptic side, you know, I started off my work back when I was just a grad student working with these kinesthetic type devices that are grounded, that mostly sit on a tabletop. So a stylus-based device that you would interact with a virtual environment. And I'm interested in how the haptic feedback that we provide through that grounded device can train people to learn new skills. So here we're using an exoskeleton to train a task where you're controlling the trajectory of a double pendulum. You can feel all the dynamics of the pendulum, but you're also getting assistive forces from a haptic device, either this kinesthetic device or a wearable device. We've applied haptic feedback for training of surgical skill. I'm going to talk with Blake about that on Friday. We've looked at how the user can provide input to a robot to change robot behavior. And then we've also looked at applications for prosthetics. So can we augment human performance with a prosthetic device by adding additional haptic cues? So that's just kind of an overview splash of a lot of the things going on in my lab, but now let me dive into my topic for today. So first, I have to thank the people who actually did the work. So this is my current set of students. These are PhD students and master's students and undergraduate students. But specifically today, I'm going to highlight primarily the work of Jenny Sullivan, who's a former research assistant, and Nathan Dunkelberger, who's a PhD student. And then I'll just touch on a little bit some current work of PhD student Evan Pezent, who will be heading up to Seattle to work at Facebook Reality Labs in March. And then Zane Zook and Joshua Fleck. And then this was funded, the work I'll talk about today was funded by NSF and Facebook Reality Labs. So the application I wanted to talk with you about is a challenge that we were sort of presented with from Facebook, which is, can we use haptic devices to enable communication? And specifically, not just like notifications from your smartwatch or you know, your navigation system buzzing and telling you it's time to take a right turn, but really, can we take the English language and encode that as haptic cues that people can learn to perceive and then understand those messages? And the motivation for this might be perhaps you want a mechanism of communication that's more private. You know, when we pull out our phones to read our text messages, people could see it over our shoulder. It could be in a military scenario where you want private communication, but it could also be kind of augmenting the information we're already receiving. So it could be a duplication of what we see visually or what we hear, or it could be a channel that we use when our visual channel is overloaded. So lots of different scenarios that we see as possibilities for wearable haptic devices that can be used for communication. So I'll talk just a little bit about haptic perception. So in our skin, there's a number of different mechanoreceptors that respond to different cues. So here's just a cross-section illustration of the skin, and a table which shows the different haptic mechanoreceptors. So we have Pacinian corpuscles, Ruffini endings, Meissner corpuscles, and Merkel discs. And each of these mechanoreceptors responds to a different kind of stimuli. So our Pacinian corpuscles respond to vibration primarily, whereas our Ruffini endings respond to skin stretch or lateral forces. And for example, also the Merkel disc respond to pressure or textures. So we have all of these different mechanoreceptors in our skin, but still if you think about most wearable devices, I mean, I'm wearing my like Samsung watch here, and all it does is vibrate. So most of the devices that are out there have been focused on just the vibration aspect of haptic cueing. So my laser pointer just keeps disappearing. So we'll just carry on here. Oh. All right. So here's some examples of different wearable devices, and I'm showing first the vibration devices. So let me try that laser pointer one more time. So here's a couple different examples. So most vibration devices are things like sleeves or vests. So we embed an array of vibrotactile actuators. It could be different types. We put them in sleeves or vests or belts. And these devices are really appealing because it's really relatively easy to fabricate them and control them. And when you design your haptic cues, you have a lot of different knobs you can turn, right? So you can vary the amplitude, the frequency, and even the sequencing of these individual tactors to create what I would call most vibrotactile gestures that you can feel on the body. Skin stretch devices are another type of wearable device that's intended to, elicit responses from the other mechanoreceptors besides those that respond to vibration. So a skin stretch device can be something like a lateral skin stretch, which might go across the skin this way, or a twisting kind of device, not so much that it's painful, but just a cue as such. So this is a device that was presented a few years ago. And the last kind that we are seeing a lot of is this radial squeeze. So it's really like a cuff or a wrap that comes around the limb and tightens, so you feel a squeezing effect. So you might think then we have all these different mechanoreceptors in our skin, and each of these devices is sort of targeting a different kind of mechanoreceptors. Let's just combine them and we'll come up with something that's better. So multisensory haptics is this idea that we're going to take advantage of those different kinds of mechanoreceptors, and we'll use a combination of haptic actuators. For example, here I'm showing how we've combined a squeeze band, a skin stretch device, and vibration into a device we call MISSIVE, which I'll talk extensively about later today in the rest of my talk. But maybe more is better, right? So maybe if we can vary the types of cues, not just depend on vibration arrays where we're modulating amplitude and frequency and sequencing, maybe if we combine these with squeezing and stretching, we can get a richer set of cues. We're not the only ones to do this. So another example is some work by Domenico Pratachizza's group in Siena. So they have this device, looks almost like a torture device, but it's not really. So it's a mechanism with two radial squeeze devices, so that you can do around the arm, but there's an actuator between them. So you can actually pull apart or pull together these two devices. And then you can also, because each squeeze band has two actuators, you can do twisting as well. So you can tighten and then you can twist the band, kind of giving that skin stretch effect. And you can do this together or apart. And they use this device to provide some intuitive haptic feedback in a teleoperation scenario. Right? So my group is not the only one starting to think about combining these stretch and squeeze cues in unique ways to enhance the number of types of cues that we can provide to users. So we were approached by Facebook for this problem of, can we develop a haptic device for communication? And they were specifically interested in this work that we had been doing in starting to combine multisensory haptic cues into single devices. So the problem laid out to us was they wanted us to go with a multisensory approach, and they wanted us to keep the footprint of our device small. So no sleeves, no vests, no arrays. We really had to keep a small footprint, something that was like wearable, maybe a little bigger than a smartwatch, but something that's more in that form factor. So the approach that we took for this problem was to kind of break it down in the following steps. So first, what language components are we going to use? There's lots of different options for what we actually want to encode and transmit. What hardware are we going to use? We kind of already knew the answer to that one, but it makes a better story to go this way. And then how are we going to implement language through that hardware and train users and assess the approach? So when thinking about how we're going to encode language, there's a number of different options. So you can think about, as electrical engineers, maybe the first thing you're thinking about is the signal content of sound, right? We've got varying frequency and amplitude, and that makes up the sound waves that are processed in our ears and by our brains to understand as sound. But if we think about English language, there's other ways to break that down. So you could imagine recording and transmitting a continuous signal that represents frequency and amplitude of the sound. But we can also think about how language is encoded through things like letters, phonemes, or words. And I'll talk about each of those in a minute. Some of the trade-offs with these different approaches are what's required in terms of the number of cues that we have to present. Should we choose letters, phonemes, words, or acoustic components? The speed at which we can transmit that information, and how intuitive it is for the user to learn. So if we think about acoustic frequency, the haptic representation is actually pretty easy to translate, right? We are controlling vibrotactors, which are much like speakers. So we can really just play almost sound through the vibration actuators. The transmission rate is real time, but some groups that have tried this approach have shown that it's very, very difficult to learn. For example, 70 to 80 hours of training to learn a vocabulary of just 60 words. So it's great because it's completely open-ended, right? You have no limits to the size of the vocabulary, but it's not intuitive because this is not the way we sort of understand language in terms of forcing the processing of the frequency and amplitude components. So we ruled out this approach. If we think about letters, the haptic representation would be, we need 26 different cues to do letters. So the information per cue is low. It's sort of the smallest building block, very intuitive. But to convey something like the word house, you need 5 cues for a single syllable word, right? So there's some drawbacks to letters as well. Phonemes are another sort of building block. They're sort of the parts of sound. So if we look at the word house, it's made of actually 3 phonemes: the phoneme for h, the phoneme for ow, and the phoneme for s, the letter S. And so you only need 3 cues to transmit the word house by phonemes. And but the challenge is you need more cues, right? We need, depending on your dialect and your accents, 39 is one set of phonemes that is sufficient for the English language. So it's a medium level of information per cue, and there's some intuitiveness here, but if you look at the representations of phonemes, it's not as natural to us as sort of just reading letters strung together as words. But you could also go to just symbolic representations of words where each haptic cue might be a word here. So you have high information per cue. It's very intuitive, but you need an exhaustive list of cues to map to all these different words. So if we put that all together, we think about acoustic frequency components versus letters versus words versus phonemes. There's sort of, I've given like a buzzer X to one thing in each of these. So letters we felt was too slow because more letters are needed than to transmit a word than phonemes. Words just requires too big of a cue set, and acoustic frequency components is too difficult to learn. That leaves us with phonemes, which is the approach that we took.
Hey, Marcy, can I quickly interject?
Sure.
There was an interesting question on the chat about if you happen to know how hard it is to learn, or the kind of, throughput rates and things like that for Morse code.
That's a really good question. So there are some groups that have used Morse and Braille for tactile representation of words, and the performance is comparable to letters. One advantage of Morse and Braille is that they are really well suited to these vibrotactile displays or tactile arrays that you can feel. We sort of ruled that out again, partially because they were pushing us to phonemes and this multisensory approach, but also because of the transmission rates, because you do 1 per letter. All right, so we're settled on phonemes for better or worse, and I can talk more about that later. And now we needed to determine what hardware are we going to use. We have to convey 39 cues to use phonemes as our building block for language. So here's some previous approaches that have been presented. Most all of them, really, for language transmission have been fully vibrotactile. So we have a glove here where they did vibrotactile feedback on the fingertips and in the palm. We have a sleeve here which is doing an array of vibrotactors. So Hong Tan and Charlotte Reed at Hong is at Purdue and Charlotte's at MIT are really active in this area right now. And they're taking the tactor array approach where they have a sleeve. And then we have a vast array that was presented by Novich and I see his face, but I can't think of his name. Scott Novich is the lead author on that paper. David Eagleman was the other guy. So what we found was these all take these large areas, and while we can come up with a lot of different tactile representations or cues for phonemes, we were really trying to explore what our multisensory approach could do. So the strategies, again, with these vibrotactile arrays is to kind of make these gestures. So Novich made a vest, and he sort of used these motions across the array of tactors to convey different cues. And Charlotte and Hong Tan have this sleeve, and you can see they've even put in some of their cues. So as the vibrotactors are stimulated down the sleeve, the one that goes sort of toward the wrist or away from the wrist, one of them is ooh, right? And so they sort of conjure up these feelings. I think like you're tasting something delicious goes around the arm, whereas other cues might be shorter in duration that could be like consonants that are like the letter T, right? Short and crisp. So they really make these gestures that are reminiscent of the sounds that correspond to the phonemes. So our approach was to use this MISSIVE device that we've developed, which combines vibration, stretch, and squeeze, and map our phonemes to the different cues that we could produce. So let me show you a little bit of an intro to this hardware. Oh, it was going to run. Well, the laser pointer is not as great as I can't make my video run with my laser pointer on. Here we go. I'll figure this out in just a second. Okay. So this is our MISSIVE device, a great acronym, better than my lab acronym. And it's combines stretch, squeeze, and vibration elements. So from stretch, it's bimodal, either it's on or it's off, binary. The squeeze is the same, on or off. And then with vibration, we have 4 tactile locations. We've designed 3 perceptually distinct patterns, and we've demonstrated through some pilot testing that you can reliably perceive these different cues. So let's walk through them. So our hypothesis is that using a multisensory device instead of a single sensory or vibration only device will allow for better cue identification accuracy, because the cues are going to take advantage of the multiple types of mechanoreceptors that are in the skin. So we wanted to test this as a starting point into this world of phonemes. So we compared MISSIVE cue identification to identification of cues that are only comprised of vibrotactile elements. So kind of the side-by-side comparison with MISSIVE, we have a haptic rocker that we use for lateral skin stretch. That's demonstrated in orange. Then we have a squeeze band. So those are each actuated with just servo motors. The squeeze band tightens the band. That's illustrated in green. And then we have a band of 4 vibrotactors. So in our MISSIVE device, you have some combination of a vibration cue, a stretch, and a squeeze. And in our single sensory device, we kept the vibrotractor band exactly the same. And then instead of stretch and squeeze, we inserted 2 additional vibrotractors. So one that would be activated in place of stretch, and one that would be activated in place of squeeze. And so we have cues that last a maximum of 350 milliseconds. And we have 32 total available cues. So squeeze can be on or off. It's the longest cue in time because of the amount of time that it takes our servo motor to fully squeeze and return back to neutral. Our skin stretch is activated by this haptic rocker, again, on or off. And our vibration cue, we use a C2 tactor, and we have a short duration, 50 milliseconds, a long duration, 150 milliseconds, and then the 4 different locations around the band for that vibration cue. So altogether then, we can get 32 available cues with MISSIVE. And for the single sensory device, instead of squeeze, it's a second vibrotractor. Instead of stretch, it's a third or an additional vibrotractor. So the single sensory device has 6 vibrotractors in all. So to compare our ability to identify cues with these devices, we conducted a repeated measures crossover design with 12 participants. They were self-paced through 2 different training phases, both exploration and practice. And then we had a testing phase, which consisted of 5 repetitions of each of the 32 cues. We had them complete a survey, and we randomly assigned them to either do MISSIVE first or the single sensory device first, and that was the crossover design. So everybody did both devices. The setup looks like this. So the participant sits at the computer wearing noise canceling headphones, playing pink noise. They have MISSIVE on the arm, or they have the single sensory device, and they're interacting with this GUI interface through the different stages of familiarization with cues, training, and testing. The visualization looks like this. So we have this sort of circle figure on the left, which represents the 4 different vibrotractor locations, and either high for long or low for short. Then we have the rocker, which looks like the pizza in the center, where if it's activated, it's rotated, and if it's not activated, it stays neutral. And then sort of the donut on the right, maybe I'm hungry, and that's why I'm using all food analogies. All right, so on the right, we have the squeeze band, which is either squeeze so it's small or no squeeze so it's big. Right? And the way we tested is that each test cue was presented between 2 masking cues. The reason we did it this way is because we were anticipating the application of speech transmission, where you would be getting successive cues in a row. And so we wanted you to ensure that you could identify a cue in sort of a string of cues. So we gave 2 random cues, first and third, and you were asked to identify the middle cue. Let's see, so you got 10 minutes to train. During training, you could freely move between a familiarization interface and a self-test interface, clicking icons corresponding to each component, and then feeling the cue on your arm. And then self-test had correct answer feedback, where we would give you a chance to practice the kinds of presentations you would get in the testing. And then the actual evaluation. So testing was 160 trials. That's 5 repetitions of each cue in a randomized order. So I've got a video here that shows how this looks. So here's the user kind of working through this completely independently. So they're clicking what they want to feel, and then they hit the play button, and then the devices are actuated on their arm. So they can test different combinations of squeeze, no squeeze, stretch, no stretch, the different vibrotractor locations, and the short and long cues. All right, so that's the process we use. So the mask, the cue, then the mask. And so here they're getting correct answer feedback. Nathan got that one right. And so you can see the actuation and then guessing what he felt, and got that one right. All green is the correct answer feedback, and then trying again, some stretch, squeeze, and missed a couple of those, right? So they can see their performance. So again, they did this for the single sensory device and the multisensory device, the same interface. It was just represented as the rocker and the squeeze, even when it was replaced with a vibrotractor. All right, so these spider plots show the true positive rate. So remember that these cues are combinations of vibration, stretch, and squeeze. So to get it correct, you needed to get all three components correct. All right, so on the left-hand side, we have around the spider plot are the different vibration components. So there's two that begin with T are the top vibrotactor, the two that begin with B are the bottom vibrotactor, and then right and left, high and low for the short and long. And then along the bottom row, we have the condition for stretch or the top vibrotactor in the proximal band, or squeeze the bottom vibrotactor in the proximal band. So what you can see just by looking at the first plot, now this is when participants were only receiving vibration. The stretch and squeeze or the corresponding tactors are not being actuated. And you can see here, their performance in the multi-sensory case is better than the single sensory case, even though it's the identical types of cues. And we think that this is because there are other vibration cues that they're trying to perceive that are replacing the stretch and squeeze. Then what we can look at in these plots is their performance when either stretch is on, squeeze is on, or both are on. And you can see the performance really degrades here. So their ability to correctly identify all components of these multisensory cues is diminished, but it's better in the multisensory case. It's a bigger area of purple than in the single sensory case. And there's also, we see that like if you look in the leftmost one, actually in all of them, the orange ones are sort of pointy stars. It basically means that they're better at identifying the vibration that's longer than the vibration that's shorter, right? Which also is somewhat intuitive. But this representation doesn't paint the whole picture. And that's why I like this ladder chart instead. So what I'm showing here, down the center is all the different cues. So in gray are the 8 vibrotactor cues when it's only vibration. When you see that the set of 8 in red, that's vibration plus squeeze. When you see the set of 8 in blue, that's vibration plus stretch. And when you see the set in purple, that's vibration plus stretch plus squeeze. So all three together. Down the center is the cue that was presented to the participant. And so then on the side where you see the picture of MISSIVE, that's the response when they had MISSIVE on. And on the side where you see the single sensory device, that's their response with the single sensory device. So what we can notice first is that for the vibration only case, people are pretty good at this. The thicker the line, the more they responded with that answer. And you can see that people are able to correctly respond with the correct vibrotactor and the correct cue, short or long. Right. So in the previous slide, we had to get all the components correct. But in this one, what you can see is where the errors were made and what they were guessing instead. Right. So now let's look at the left-hand side. So these are the cases where we're cueing multiple vibrotactors. So they're getting the cue from the vibrotactor band plus one or both of the additional tactors. And you can see that they're making lots of errors now. They're making errors, they're mixing up which tactor they felt in the band. And they're also mixing up whether they feel the top or the bottom tactor in the proximal band. When we look at the same performance for the MISSIVE device, the errors that they make are very systematic, right? So in the case of the vibrotactors plus squeeze, the red lines, they're all horizontal, which means they're picking the right vibrotactor in the presence of squeeze. In the blue, they're all horizontal. They're picking the correct vibrotactor in the presence of stretch. Now, when you look at purple, they're picking the correct vibrotactor some of the time in the presence of stretch and squeeze. But all those diagonal lines mean that the user is missing the stretch cue, right? So they're saying when presented with vibration, stretch, and squeeze, they're identifying it as vibration with only squeeze. So it's a very systematic kind of error, which gives us some insight into how we might better design MISSIVE to have more salient stretch cues so that they're not masked by the presence of squeeze. But this also gave us a lot of information about which combinations of stretch, squeeze, and vibration would be most useful for our application of mapping phonemes. All right, so let's return now to that problem. So we are going to use phonemes. We like MISSIVE. People are really good at identifying these multisensory cues. So how the heck are we going to implement language through this hardware? So we went back to our set of cues, and instead of 32, we developed 48. right? So the difference is it's still squeeze on and off, it's still stretch on and off, but for vibration, we added a double pulse. So now we can have a short cue, a long cue, or a double pulse. Now, we had done some testing with this scenario prior, and the reason we didn't do it in the comparison study is really just a hardware limitation for the all vibration device. I'm happy to answer questions about that. But we have a set of 48 cues that we know people can reliably discriminate in the multisensory device. So now we have to pick 39 of those cues that are best suited for our phonemes and figure out how to match phonemes to cues. Right? So the way we're going to do that is rely on collaborators who are experts in machine learning, right? And what we did was we first made the decision that our vowels would all have squeeze. And the reason we did that is because if you think about vowel sounds, they are temporally longer than most consonant sounds. And the squeeze cue is longer than cues that don't have squeeze. So we just thought, okay, this is an intuitive way to differentiate consonants and vowels. So all vowels will have squeeze and all consonants will have no squeeze. So a vowel cue could be always squeeze, one of those vibration locations and patterns, and sometimes also stretch. Now consonants then are going to be one of those vibration patterns and sometimes stretch, but never squeeze. So our collaborators developed an optimization algorithm to determine the mapping between haptic cues and phonemes. So we had data already from our comparison study about common confusion patterns between the multisensory haptic cues. And we mapped such that if there was a common haptic cue identification error that occurred, the corresponding phoneme confusion would not produce a word that could logically replace it in context, right? So to state that another way, we optimize the cost function shown here. N represents the set of phonemes. We have 39 of those. M represents the set of cues. We have 48 of those. D is the probability of confusing one haptic cue for another. F represents the cost of confusing one phoneme for another. So we have this constraint then of vowels mapping to squeeze cues. I, J represents a phoneme pair, and psi represents the particular mapping of phonemes to cues. So we're looking for a mapping that minimizes this overall cost function where we're penalized for haptic cue confusion and phoneme confusion. So they ran through the entire possibility of mapping with these 48 cues and 39 phonemes and gave us the output, which is represented on this slide. So what we have in this figure is on the right-hand side where you see green, that is squeeze on. So all of those phonemes are vowels. And you can see A as in act, I can't read my tiny screen, oi as in oil, as in earn, aw as in awful, right? So now you can understand how dialects and accents can come into play here, but we'll just call it the Texan set of phonemes. So all the ones in green include squeeze, and they're all vowels, and they may or may not have stretch. And then all the ones on the left are vibration, and many of them also with stretch, right? So that's all of our consonants. Now that's all 39 phonemes. For our experiment, we were working with a reduced set because we were given a list of words that we needed to train people to learn. For that list of words, we only needed 23 phonemes. So we used a subset of that whole set and trained people to learn these haptic cues and their phonemes, and then put them together into words. So our training protocol is in tiny little print there on the left screen, but I'll walk you through it. We did a study with 16 participants, 7 female, average age of a graduate student. Then we had our bands, and we trained the phonemes in sets based on the tactor location. So we trained set A first, which was all the phonemes with the top vibrotactor active, then B, which is the side, then C, which is this bottom, and then D, which is the other side. All right. So you can see our training protocol as we go down through days. You can see we're adding those cue sets. So in day 1, we only do set A. And in day 2, we start with A, and then we add in B and C. And then in day 3, we add in D. And then in day 4, we test them all. On days 1 through 4, the participants end with a multiple choice assessment of word recognition. So they learn the cues, then they learn the phonemes that go with those cues, they get introduced to simple words, and then they have a post-test, a multiple choice test where there are 12 options and they're picking which word they feel, right? And that happens over 4 days, and the total amount of training in those 4 days is 100 minutes. Then we had 5 participants who continued for an additional 60 minutes of training over 4 additional days. And instead of having them do multiple choice at the end, we had them do a free response. So we didn't want to give them the advantage of being able to guess, right? So here's an example of the 50 words on an untimed post-test at the end of day 4. These words had an average of 3 phonemes per word and 4 letters per word. And so you can see things like baby, free, moment, room, sob. All right, so these are the kinds of words. And on days 5 through 8, our final tests had 75 words each that were comprised of the same 23 phonemes. So we had a vocabulary that we could create with that. And it's fun to talk about which phonemes we left out and what words were then left out. All right, so let's look at phoneme recognition on day 4. So this is a confusion matrix, and what we have at the top is the actual phonemes that were presented, and on the left is the user response. And you can see a very strong diagonal, which is what we'd want to see. This is the quadrant where squeeze is on. So those are all of our vowels. And if you notice, the recognition there is not as good. There's quite a bit of confusion and errors between vowels. And then down here is all the ones with squeeze off. So those are all consonants, right? And you can see the recognition for consonants is quite good. All right, so we can see here the different phases of learning that our participants go through. See if I can find my mouse again. There we go. All right, so here's a user just clicking. They're learning the phonemes. So they're clicking on the phoneme, and then they're playing the cue that goes with that phoneme. Right? And you can see, again, this is the first set. So it's only those phonemes that go with the tactile location at the top of the band. Once they've learned the phonemes, then we go to testing phonemes, right? So here, now they are playing a cue, and then they're guessing which phoneme it is. And then they can check whether they were correct or not. So we give correct answer feedback. They can replay it. And we're evaluating their ability to identify the phoneme that goes with the haptic pattern that they felt. And then finally, we test words. So here they play one phoneme at a time. So you click, click, click to get each phoneme. And then you see the menu of possible words. And then you would guess the word. So let's play that one again. So they're playing the phonemes. And once they've played all the phonemes, then they get the possible words that they're selecting from that set. All right, so these are our pre-test results. So pre-test means the beginning of each day. All right, so we have days 2, 3, and 4 for 11 of our participants, and then the 5, 6, 7, 8 are the 5 participants who continued on. So you can see on day 4, the accuracy in phoneme recognition was 61.4%. And then after 60 more minutes of training, we got up to 85.2% accuracy with our second group. And the learning did seem to level off with that training beyond that day. Post-test is how they perform at the end of each day. So this is the word recognition accuracy with post-test. Again, days 1 through 4 is multiple choice, and days 5 through 6 is free response. So we would expect some loss of performance when they go to free response. So we see averages in green, and error bars represent standard error. And we can see that the performance reaches almost 90% with the multiple choice on day 4, and levels off at about 70% at day 8. So kind of summarizing this study, after 4 days and 100 minutes of training, they could identify phonemes with 61% accuracy and words with almost 90% accuracy multiple choice. With 4 additional days and 60 more minutes of training, their phoneme identification accuracy went up to 85%, and their word identification accuracy went to 70%. So this is kind of where we're at with this study. We're doing a couple of things to kind of move on. So one is a lot of the errors were with vowels. And part of that is because the vowels involve squeeze, which can mask vibration and stretch. So there's an error on the haptic perception side. And there's also just a really non-intuitive aspect of vowel phonemes. They are spelled funny. They don't correspond to how words are spelled. I mean, English spelling is bad enough. So it's challenging to kind of put that together. So I have a student who's pursuing this with letters. So even though we may have to have more cues, maybe it's more intuitive to spell out words with letters like Morse code or Braille. And he's actually finding really good results with that approach. We've also redesigned the hardware to overcome some of the perceptual saliency and masking problems that we saw previously. But we're also looking at some other applications of these multisensory devices. So I'm just going to do a little bit of a diversion here for a few minutes to show you some of the other work that's going on. So my students Zane and Joshua have been really diving into the psychophysics of these multisensory cues. So they developed this fixed test bed, we call it the Ames test bed, that you put your arm into, and we have modules. So we have a squeeze module and a stretch module, and we can put vibrotactors in there too. And they're very, instead of just servo motors, these are like Maxon motors with encoders, and we have force torque sensors. So it's all very well instrumented so that we can track what's happening with these cues. So we're looking at the sort of mechanics of interaction between the modules and the skin, but we're also looking at the perceptual performance. And what they've done is look at the just noticeable difference in stretch and squeeze with and without an interfering cue. So what we have on the top plot over here, I'll just have to use right and left. So in the top row, we have 2 plots. We have a bar plot and we have this sigmoid function. The bar plot is showing the just noticeable difference for squeeze, and then for squeeze when we have an interfering stretch cue. And if you're looking for a difference, you will struggle to find one, right? So it's not different, right? They're not, and that's like not a statistical thing, but it appears that stretch cues do not interfere with our ability to perceive just noticeable differences in squeeze. Contrast that to the plot below. Now we're looking at the just noticeable difference when we present a stretch cue alone. So how different do the magnitudes of stretch need to be for you to perceive them as different? And then when we squeeze, interfere, and you can see that the just noticeable difference goes up significantly, and that is statistically significant, right? So our ability to perceive differences in stretch amplitude is significantly affected by an interfering squeeze cue, which is exactly what we saw in the MISSIVE study with the multisensory compared to single sensory device, but now we have the psychophysics to show it. And you can see the same thing with the sigmoid functions. These are the curves that we create to determine the just noticeable difference in stretch magnitude. You can see the blue and the green in the top don't look very different because they're not, squeeze is not really affected by an interfering stretch cue. But in the bottom, you can see that for small amplitudes of stretch, when we have an interfering squeeze cue, we really mess up their ability to perceive those differences in magnitude. So this is some ongoing work we've got with the psychophysics. We've also looked at how the amplitude of the interfering cue affects perception and how the distance between cues affects perception. Another fun thing that we've been working on is using these multisensory devices in VR. So this is the TASB bracelet. This was developed by my student Evan Pazent in collaboration with Facebook. It's a tactile and squeeze. So we gave up on stretch with this one because it's not as reliable. So we just squeeze and vibration, and it provides a vibration at 6 different locations around the wrist. And then it also has a squeeze effect. And the squeeze is done through this cool mechanism. It's a brushless motor and a pulley and cable system that tightens the cable around the wrist, squeezing with quite a bit. I think we can do up to about 15 newtons of squeeze force around the wrist. All right, so that's what TASB looks like. And Evan's been working on implementing TASB in virtual environments. So I'm gonna let him talk about it, and I'm just gonna play this video.
Our approach to creating believable interactions has 3 parts. First, haptic vibrations render discrete events such as hand collisions, impacts, and high-frequency content. Second, we use proportional squeeze for continuous forces such as object stiffness, weight, and inertia. Finally, visual pseudo-haptic effects manipulate the virtual hand position to give the illusion that certain actions require more physical effort. Let's take a look at some examples. In this button interaction, vibration is rendered when the user contacts the button's surface and fully depresses it. Squeeze increases as the button is pressed to convey a spring stiffness. In fact, by increasing the rate of squeeze and the intensity of the pseudo-haptic effect together, it is possible to make buttons that feel harder to press. Vibration, squeeze, and visual pseudo-haptics can be applied to other motions such as pulling and twisting.
All right, and he's got an application I'll let him talk about too.
CASB is most compelling when haptic feedback is provided on both hands. This is especially true for two-handed interactions that simulate reactive forces between the hands, such as this bow and arrow example.
So what's neat about this application is when we combine these multisensory haptic cues with the pseudo-haptic visual illusions, we can create some pretty believable substitutions for interactions that would otherwise occur at the hands and even the fingertips. And we feel that this work really highlights an opportunity for overcoming the typical low fidelity cues of wearable haptic devices. So the application of MISSIVE that I talked about, those cues aren't trying to recreate reality or make it feel like you're interacting with a virtual environment. They're simply patterns of haptic cues like notifications on your smartwatch that are encoding information, in this case, phonemes. Here, we're really trying to use wearable, and what I wanted to say about that is that they don't need to be super high fidelity, right? We can use servo motors, we can use these simple binary stretch, squeeze, and vibrations. But if we want to add haptics to VR environments without bulky gloves or exoskeletons on the hands, we really need to think about how do we take advantage of lower fidelity haptics combined with pseudo-haptic illusions to really recreate these sensations. So I see this as an opportunity to really overcome the low fidelity cues that are typical of wearable haptic devices by leveraging the manipulability of the visual display to do things like improve realism, immersion, and the salience of the haptic effects. And so if you can combine that with our understanding of human perception of these multisensory cues, then you really have an interesting opportunity to design novel devices for exciting applications. So just to kind of wrap up then, I spent most of my talk talking about multisensory haptics for language transmission. What I like about these multisensory haptic devices is they really take advantage of the different mechanoreceptors in the skin, presenting cues simultaneously that are still salient and reliably identifiable by participants. The language transmission study is really perfect for this challenge of needing large cue sets that really drive us to these multisensory devices. So they work well, and our participants were able to learn a language, a vocabulary of 50 words with just under 100 minutes of training with fairly reliable recognition accuracy. So with that, I'll conclude and take any questions.
That was really fantastic. There were a bunch of super interesting questions in the chat. I'll try to summarize, but the askers could raise their Zoom hands or just interject and kind of overlap. Howard, looks like you unmuted.
Yeah.
Yeah, go for it.
So I'm wondering if all the information has to be transmitted. My example would be Hebrew, where in the written language, the vowels are not included. It's all consonants, and the person at the other end interprets it because they have shared knowledge with the sender.
Except for kids.
Except there's a version for children and new learners where they add the vowels. And I'm thinking that for your system, that might be a way to really reduce the amount of transmission and the number of phonemes that you have to haptically represent.
Yeah, that's a great suggestion, and something I'll be certain to look into. And we sort of see this happening because even though we get a fairly high rate of phoneme confusion, people are still able to figure out the words, right? They're using the context of the consonants to guess, even if they didn't correctly identify the vowel phoneme. So it kind of speaks to the approach that you described. So yeah, thanks for that suggestion. I think that's could be a really interesting strategy to take.
I'll jump in with another one.
Okay.
Thanks, that was so much fun to think about and look at the results. And actually, I thought 70 to 85% was pretty darn impressive.
I mean, it's better than I think my teenagers do when I'm talking.
Yeah, so my question was, when you were designing that 5-day training or 4-day training protocol, what kinds of principles did you think about for maximizing recall and learning?
So great question. And actually, let me go back to that slide so I can have it to lean on. Actually, it'll be better if I do it this way. So we debated, so one of the biggest decisions we had to make was, is it important for people to know the cues before we map the information? So we spent, you can see here, there's a whopping 10 minutes of learning haptic cues. So we let them play around with the different combinations. Through some really rough, very small end pilot testing, it didn't seem to matter whether you specifically trained people to recognize, oh, that was top long vibration with squeeze, or if you just said, here are the different cues you're going to feel, and they're encoding these phonemes, and which phoneme did you feel? I actually have a student who's going to dive into that more deeply. It's really an associative learning task where you're trying to associate visual information, the phonemes on the screen, with haptic information, the patterns on your arm. And there's quite a bit of literature that should indicate that prior exposure to the haptic cues would improve your rate of learning the mapping to the information. So that was something we just kind of had to make a choice because we were really on a short timeline. The other thing that became evident was in some pilot testing, we did a whole bunch of phoneme test training until they had the whole phoneme set and then did words at the end. And they were kind of overwhelmed by having to put the phonemes together. So doing this process where we sort of did these chunks of vocabulary and put them together into words was also something, again, pilot testing, but that was a philosophy that we found to be quite successful. And I was talking with somebody earlier, actually it was Christy. So we were talking about our kids learning to read, and we used these Bob books, these little scholastic books where like the first book only uses the ah sound. So it's a whole book about cat and Matt and Pat. And I was like, well, that's the way we should do this. Like my kids learned, a certain set of vowel sounds and put together all these words with consonants, and then we can build up that way. So yeah, I would credit the Bob book series too for our approach.
Yeah, I was imagining like Duolingo for haptics. Yeah. That's great.
Another interesting question from the chat, this was from much earlier on, in terms of thinking about different encodings or different inspiration for encodings, was about whether you'd thought about connections with sign language. And I could interpret that question two ways, either in terms of the vocabulary, although it's actually a pretty extensive vocabulary. I studied it in high school. It's thousands of words or something like that. Or another way to interpret that question is, if you, not with the device you have, but if you instrumented the hand with proprioceptive, sort of stimulate, could you literally make people feel the sign and then in that way communicate with them or something along those lines?
I think that that's a really exciting idea. And again, we were kind of pigeonholed into our approach by our sponsor. So there's definitely drawbacks to phonemes. As I mentioned, they're hard to interpret. I think with the sign language, the challenge, right, is a device that's going to be able to form the hand. I mean, there's a lot of research into hand exoskeletons right now, and we've tried to. It's a hard problem, and so maybe maybe if it was only a vibro-tactile gloves, it would be easier. Sign language is interesting because it sort of has both of those, right? It has the whole building block letters components, but then it also has these representations that are more gesture-like. for words. I will say, where was I going to go? I was going somewhere with, it wasn't a question, but I was just going to interject it because it was an interesting debate we had. And that was, should the haptic cues be intuitive? So one of the undergraduate researchers, actually was a mechanical engineering undergrad, but he had taken some classes in linguistics. And there's a lot of study about the placement of the tongue in the mouth, the shape of the mouth. And that's actually an approach that Hong Tan and Charlotte Reed have used with their vibration sleeve. So they really thought about the, all the ooh, ah, long vowels are like strokes along the arm, right? And all the ones that require placement of the tongue towards the front of the mouth that are shorter were like these short little cues. So they went for these like intuitive haptic cues that kind of went with what we know about the formation of those sounds in the mouth. And we actually got in a huge debate with our machine learning colleagues, because in addition to being sort of forced to use phonemes and forced to use this multisensory device, Facebook really wanted us to use machine learning, right? Because I mean, it's the answer to everything. And so they pushed us to not use an intuitive mapping, because they were also funding the Purdue MIT team. And they were like, well, we already are doing that. Let's see what this other approach can do. And it turns out, let me see if I have the slide. So we looked at kind of the, so this is the cost for different mappings. So they did all these different mappings of phonemes. And so the blue is sort of the distribution of cost for random maps. And then the red is their cost for their like optimal machine learning map. And when we had them do, so we forced them to do the vowel consonant thing, the red line only moves a tiny little fraction if you force the vowels and consonants to be squeeze or no squeeze, right? So that wasn't part of, I mean, they can run this algorithm without that constraint. But interestingly, like the cost of an intuitive map was more in the random range. So we actually think that this machine learning mapping is better because it helps keep the haptic cues that go with phonemes like more perceptually distinct. So they're really unique in what they are. And the people who tried different ways of learning them really didn't indicate any preference for one or the other.
Interesting. Sorry, just a little bit under the hood. So this cost is like a loss function that's based on the statistics of the sort of false positive, false negatives that you collected?
Yes.
Cool.
So there's two parts to it. One is we looked at, so I don't have it in here, but we have a similar so this is a confusion matrix for phoneme errors. So we provided this to the team. And so they looked at when we have cues that map to phonemes that are often confused, we wanted those to be such that they wouldn't make sense in context, right? So if you can think about like, I'm trying to think of two words that have the same consonants but different vowels. So you would want only one of those to be like a real word, if that makes sense, right? So the combination would not make sense, would not create an actual word. And then we also fed them the confusion matrix for the perceptual cues themselves. So sort of the data under the hood. I didn't show it here because it was in we didn't. It's like. Well, we had it in confusion matrix form, but it was basically, where is it? There. Basically these results, right, in a confusion matrix where when we present them with a set of cues, what errors are they making? And so we tried to minimize, if there were common haptic cue confusion errors, we didn't want those to also be common phoneme confusion errors.
Super cool. I think this is just all these interesting questions and suggestions are just highlighting like how much untapped potential there seems to be. We're such visual creatures, big parts of our brain are devoted to it. And that's, a primary way a lot of us experience the world. But I mean, I think in the Zoom era, it's highlighted how much we're missing when all we have is visual and auditory, their senses.
Yeah, I mean, this has just been, this is kind of one of those, gifts that falls on your plate. So they brought us this problem. And I mean, we complained, we did this all in 9 months. We were sort of just forced to keep making decisions. And it was like, but wait, there's this cool research question we want to go do. Oh, wait, we want to go check that out. And so now, I mean, this ended about 2 years ago, but we've continued, right? The perceptual interference questions, the pre-exposure to haptic cues question. I've got a collaborator in psychology who studies the neural correlates of language processing, especially in stroke impaired individuals who have aphasia. So he uses EEG. But we're thinking now, oh, we can do these studies for haptic language compared to visual language compared to auditory language. So yeah, I've got a lot. Fortunately, I have a graduate student who in ECE who loves sitting kind of at this space between neural imaging and signal processing. And so that's what she's tackling for her work.
That's super cool. And it's really neat to see usually I think of it, the translation between academia and industry is going in that direction. And then in this direction, they're bringing you this problem, you're solving it as best you can. And then this is opening all new research directions. Super cool.
Yeah, and I'll add, I mean, if you'll let me kind of go for another 2 minutes. So the work that Evan's doing was very similar. So Evan went to Facebook as an intern and designed that TASB device, and then came back to finish his PhD. And so Facebook is supporting his PhD research to really dig into these perceptual questions in VR. So like they're interested in it, but they don't want to invest their own research. It's a lot cheaper for them to just pay a PhD student to do it and give a few little handouts to the professor. But to really dig into like, how are we perceiving, how are we modulating the visual feedback and the haptic feedback to really convey this sense of button stiffness. And we've got some cool analysis that we can do that they would never take the time to do. So I think it's been a good collaboration.
Awesome.